work with my advertiser Peng Zhang and Aaron Gamber Jacobson from Colgate University. So we all know that network outages are common and costly and hitting the news again and again. Therefore, researchers have developed the control plane verifiers to proactively find misconfigurations before implementation. CPVs take configurations and topology as input and then check whether properties like reachability holds. And many network outages are caused by link or node failures. Therefore, CPVs that can reason about failures have been developed. For example, Minesweeper, Huoyan, and SRE. Many other outages are caused by configuration updates. And therefore, researchers have developed CPVs that can reason about configuration updates like DNA and Jingjing. But another equally important but less explored cause of network outages is external routes. Reasoning about external routes is important because it may cause multiple issues. For example, if a network leaks route from one SP to another, it is at the risk of being a free transit between those two SPs. And for another example, if the traffic of an AS is hijacked by another network, then its private data is at risk. However, reasoning about external routes is challenging since the space of external route is colossal. For IPv4, we have 2 power 33 minus 1 prefixes in total. And theoretically, every external neighbor can announce an arbitrary set of prefixes. And there are 2 power 33 minus 1 possibilities for prefix sets. And suppose we have m external neighbors, then the space size can be as large as multiplying the number of prefix sets for m times, which is really colossal. So how to handle such a colossal space? There are several methods. For one method that control plane verifiers like Batfish, they take concrete external routes as input. And if we want to use verifiers like Batfish to comprehensively reason about the external routes, we have to enumerate the concrete external routes that we input to Batfish. But as we can see, enumeration is infeasible given such a large space, such a huge space. For another method is to symbolize external routes with SMT. But in practice, we found that using SMT to symbolize external routes frees us from enumeration. But in practice, we found that SMT solving is unscalable because the SMT constraints we have generated is hard for the solvers to solve in a reasonable amount of time. So as existing verifiers are suited to reason about external routes, we design our own approach named Expresso. Before introducing the design of Expresso, I will show this example network. It has 2 internal routers, A and B, and 2 external routers, N1 and N2. And we use 3-bit IP addresses and prefixes for simplicity. Accordingly, we have 15 prefixes in total, and the space size is 2 power 30. And in the network, router A and B permits 2 prefixes from the external neighbors, that is 100/2 and 110/2. And router A sets the routes of N1 to 200 in order to prefer router N1 as the exit to reach the internet. When designing Expresso, we have several observations. The first is 2 types of equivalence in route computation. The first kind of equivalence is prefix equivalence. As in the example network, for prefix, that is prefixes that match the same or equivalent routing policies throughout the network will always be treated the same during route computation. As in our example network, prefix 100/2 and 110/2, they match the same routing policies throughout the network, so they are equivalent. And all other prefixes are equivalent. The other one is advertiser equivalence. That means for a certain prefix, whether or not an advertiser announce a route for the prefix or not do not impact the best routes for that prefix. As in our example network for prefix 100/2 and 110/2, since the local preference of routes from N1 is set to 200, therefore, if N1 has announced the routes for these two prefixes, they will always be selected as best routes, regardless of whether N2 have announced routes for these two prefixes or not. Therefore, given those equivalences, we found that although the space is large, there's only several equivalence classes, and this inspires us to follow our prior work SRE, which executes symbolic simulation to efficiently explore equivalences. This is the workflow of symbolic simulation, which takes configurations and topology as input and then executes symbolic route computation, symbolic packet forwarding, and property analysis. During symbolic route computation, SRE symbolizes the up or down states of each link and then computes a symbolic RIP, which contains failure equivalence classes. For example, NAC L1, L2 is a failure equivalence class that contains 4 failure scenarios. And for Expresso, we aim to symbolize the external routes and then compute symbolic RIPs that contains prefix and advertiser equivalence classes. And a straightforward extension to SRE to let it reason about external routes is to model symbolic routes as symbolic links. And this way, we add dummy nodes for prefixes. And we add a link between each external neighbor node and each prefix node. This way, each link the up or down state of each link represents whether the advertiser announced the prefix or not. And following SRE's way, we assign one BDD variable for each link and assigning 0 or 1 to the BDD variables indicating the advertiser advertised the prefix or not. This way, for the 3-bit example, we need 30 variables in total. But for IPv4, we still need 2 power 33 minus 1 times m variables, where the first is for prefix and the second m is for neighbors. Fortunately, we observe independency in route computation, which means that prefixes are mostly independent during route computation. And therefore, we can first use 5 variables to select the prefix, 3 for IP address variables and 2 for prefix length variables. Then we use 2 variables to select the advertiser for the prefixes. This way, the up or down state of the link is collectively represented by the IP address variables, prefix length variables, and neighbor variables. We are using less variables because some variables are reused. As in this example, for router N2, its neighbor variable, lowercase n2, is reused, and this reusage is enabled by the prefix independency. Using this encoding, for the 3-bit example, we can use only 7 variables to symbolize the external routes. And for IPv4, now we can use only 38 plus m variables to symbolize such a classal space. After the encoding, I will demonstrate how symbolic routes are propagated through the network. We begin with a symbolic prefix N1, which represents arbitrary prefixes announced by router N1. It then is propagated to router A, whose import policy only permits 2 prefixes. And this results, after applying the routing policy to the symbolic route, the symbolic prefixes change to P1, L1, neg L2, N1, because this results from intersecting the original symbolic prefix N1 and the disjunction of the Boolean representations for the two prefixes. The propagation continues until finally it passes router B's export policy and is laid to router N2. After symbolic packet forwarding after symbolic route computation is symbolic packet forwarding, which contains first converting symbolic rapes into symbolic fibs, and then forward symbolic packets. However, during converting symbolic rapes into symbolic fibs, there's another challenge. As in the packet forwarding, there are prefix dependencies due to longest prefix match principle. As for the symbolic prefix P1, L1, N1, it contains 5 prefixes, 1/1 prefix and 4/3 prefixes. And the /1 depends on all the /3 prefix due to longest prefix match. And it means that one variable per neighbor is not enough anymore. But does it mean that we need 15 variables for each neighbor now? Fortunately, we observe that the dependency is limited to prefixes having the same first bits but different prefix lengths. And the prefixes having the same prefix length are still independent. This way, instead of inheriting the encoding from the control plane, we add a dummy node for each prefix length and each neighbor in data plan. And we use 3 bits to represent the IP address and neighbor length-specific neighbor variables for the neighbors. Take this for example. This symbolic rape, it has a symbolic route, and we convert it to a symbolic forwarding row. And N1 is converted into 4 new variables. However, as indicated by L1 neg L2, the prefix length is 2, and only N subscript 1 superscript 2 is needed, which means we don't need 15 variables, which means that we don't need 4 variables for N1. We only need 1 variable for N1. And I will demonstrate the symbolic packet forwarding now. We begin with a symbolic packet header true, which can match all forwarding rules. It continues matching the symbolic rapes and being forwarded until it finally reaches router N2. For the symbolic prefix, it means prefixes whose first bit is 1 and whose prefix length is 2. And the prefix is announced by N2 but not N1, will finally exit the network. After symbolic packet forwarding, we do property analysis, and Expresso currently checks for 5 properties, that is route leak, route hijack, traffic hijack, egress preference, and block to external. And the details about how we check those properties can be found in our paper. Finally, we show the evaluation results. We've run Expresso on one of a cloud service provider. The one contains 4 regions, which has several peering routers that establish eBGP peer sessions with external neighbors, and they are connected by a route reflector. We have found route leak, route hijack, and traffic hijack on the one. And I will show the detail of a potential route hijack. It begins with SPA announcing a /31 prefix to PR1. And it is permitted by PR1's import policy, which is misconfigured because of missing a deny entry to deny this specific prefix. And the local preference is set to 200. At the same time, the connected route at PR2 is redistributed into BGP and then propagated to the route reflector. However, at the reflector, it chooses the external route because of having a higher local preference. And Expresso finds this route hijack by finding this symbolic route in the route reflector's symbolic rib. And this figure shows the performance of Minesweeper and Expresso to check route leaf free on the full topology of the CSPs1. It shows that Minesweeper uses nearly 1 day, while Expresso can accomplish within 1 hour. As Minesweeper uses a long time on the full topology, we use the separate regions as macro benchmarks to compare Expresso and Minesweeper. It shows that Expresso is generally 1 to 4 orders of magnitude faster than Minesweeper. And in summary, today I first motivate the necessity to consider external routes when doing control plane verification. And I show that existing verifiers are ill-suited to comprehensively reasoning about external routes. And I show key insights and key design points of Expresso. And finally, we use evaluation to show that Expresso finds real bugs on a CSPs1. Okay, that's all for my presentation, and I'm happy to take your questions.
Thank you for the talk. This is interesting. Can you talk more about how the tool handles communities, AX paths, and regexes?
I only show how to symbolize the prefaces in these slides, but our paper have talked about how we handle symbolic AS passes and communities. And in generally, we all know that AS passes and communities, we have regexes that match them in the configuration. And we just collect those regexes and convert them into automatons, and then compute atomic automatons, and then use Boolean variables to represent each automaton, and then to use 0 or 1 to indicate whether it matches those regex or not.
Okay, thank you.
It is inspired by Batfish.
Thank you for your presentation. I want to ask, what is the max number of BDD variables? For example, if you have 10 neighbors and you have 10 prefixes in your network, you may need to build 100 BDD variables. If you consider a community, the number of BDD variables may grow further.
Yeah, firstly, you said if I have 10 prefixes and 10 external neighbors, then I need 100 variables.
BDD variables.
Yeah, BDD variables. I don't think so, because we right here that we need only 38 variables to encode the prefixes, and then 10 variables to encode the neighbors. So that's not 100. And for the next question you said about symbolic AS passes and symbolic communities, for the data sets we are using for the CSPs1, we found that the number of variables to encode symbolic AS passes and communities won't be too much.
Okay. So what is the max number of BDD variables in your experiment?
For control plan, we only need 38 plus the number of neighbors. And for data plans, as I said, we have to enlarge the number of variables for each neighbor. But in practice, we found that only 8 variables for each external neighbor is enough.
Okay, thank you.
Yeah. And due to time limits, maybe if you have more questions, you can take it offline. And by the way, I forgot to mention, this paper actually has got honorable mention for the best paper. So very cool work.